Hello, and welcome to the second supporting video for our paper about value information analysis for applied ecologists. In this video, we'll show how to use a spreadsheet to calculate the value of sample information. As in the previous video, we'll use a frog translocation program as an example, where there is uncertainty about the presence of disease as the destination site. Now, this is the spreadsheet provided as supplementary information file number 1, and the sheet we are using is called EVSI. Remember, the value of sample information represents the improvement in management outcomes that could be achieved by reducing uncertainty through the collection of a sample of additional information. Now, value of information is a decision analytic tool. So following from the previous example, we need to specify our decision problem. We have a population of a frog species within a protected area. Our objective, which is to maximize the number of individuals in the protected area by the end of the next 10 years. And we have specified the actions available, translocation or no translocation. We have formulated hypotheses about uncertainty, so the presence or absence of chytrid fungus at the new site. We have defined our belief in either hypothesis being true, 50% respectively, and we have predicted the outcomes of each action under each state of the system. Remember, the expected value of the decision under uncertainty is that of the action with the greatest expected value, and the expected value in turn is calculated as the average of the outcomes under each state of the system, with the belief in either state as a weight. In this case, under the current uncertainty, no translocation is the best decision under uncertainty, with an expected value of 100 individuals. Now, we consider the possibility of reducing this uncertainty about the presence of chytrid at the new site by carrying out a test, for example, by looking for chytrid DNA on other amphibians at the new site. Now, the first thing we need to do is to define the performance of the test. In this case, we could use estimates published by Scarrett et al. In Journal of Herpetology in 2011. Now, the probability that the test correctly identifies chytrid if it is present, so the sensitivity of the test, is 73%. And therefore, the probability of a false negative is 1 minus sensitivity, so 27%. And the probability of correctly classifying a negative test, the specificity of the test, is 94%. And therefore, the probability of a false positive is 1 minus specificity, 6%. Now, if we perform the test, it could return either positive or negative. And we could have a positive return in two cases. If chytrid were present, with probability equal to the prior belief in its presence, and the test picked it up correctly, with probability equal to its sensitivity. Or, if chytrid were indeed absent from the site, with probability equal to our belief in that hypothesis, and the test incorrectly classified this, so the probability of a false positive. In total, there is approximately a 40% chance of getting a positive test result, including true positives and false positives. Similarly, the test could return negative if chytrid were indeed absent, with probability equal to the prior belief in its absence, times the specificity of the test. Or, if chytrid were indeed present, with probability equal to the prior belief in its presence, times the probability of a false negative. So 1 minus the sensitivity. As a result, we have approximately a 60% chance of a negative test result, including true negative and false negatives. So depending on the test results, our belief in the hypothesis will change, and we can use Bayes' theorem to calculate exactly what this change will be. We will show how Bayes' theorem works step by step. So in the event of a positive test result, what is the probability of chytrid being there? According to Bayes' theorem, the probability of chytrid being there, probability of A given B, is equal to the probability of picking up the chytrid if it is present, so the sensitivity of the test, times the probability of Kitrid actually being there, which is our prior belief, divided by the overall probability of getting a positive test result, which includes the true positives and false positives. In total, if we get a positive test result, our belief in the presence of Kitrid will go from the initial 50% to 92%. And since the beliefs sum to 1, the probability that Kitrid is indeed absent, our new belief, is 1 minus the belief in its presence. So, 8%. So how would our decision change after collecting this information? We can calculate the expected value under uncertainty using the updated belief, which in a Bayesian framework we would call the posterior. We do not expect the outcomes to change for our actions under each state. So if we translocate, we expect to get 55 individuals if Kitrid is present and 135 if Kitrid is absent. And if we do not translocate, we expect to get 100 individuals either way. So the expected value of translocation under the new uncertainty is equal to 55 individuals in the case that Kitrid is present, plus 135 individuals in the case that Kitrid is absent. Similarly, the expected value of not translocating is 100 individuals regardless of the state. Again, the expected value of making the decision after a positive test is the value of the action with the greatest expected value. In this case, getting a positive test result has reinforced our initial belief that no translocation is the best action to take. Now, let us consider instead what we would do if we ran the test and got a negative result. Again, the posterior belief can be calculated using Bayes' theorem. The probability that Kitrid is present, given that we get a negative result, can be calculated as the probability of a false negative, so 1 minus the sensitivity of the test, times the probability of Kitrid actually being present, our initial belief, divided by the overall probability of a negative test result, including true negatives and false negatives. So if we ran the test and got a negative result, our belief in Kitrid presence would change from the initial 50% to 22%, and therefore our belief in Kitrid absence would change from 50% to 78%. If we had to make the decision under this updated uncertainty, again, we would not expect changes in the individual outcomes of actions, and we would calculate the expected value of each action under the updated uncertainty as the average of the outcomes under each state multiplied by the respective weights. So for translocation, 55 times the new belief plus 135 times the new belief. And again, for no translocation, the outcome would be the same regardless of the state of the system. Now, making the decision after a negative test, we would choose the action with the greatest expected value, and a negative test would convince us that the translocation is indeed the best action and make us expect an outcome of 117.4 individuals. So what is the value of having collected this sample of information? If the test returns negative, we will expect the same value as that of the decision under uncertainty. Since it was just us doing false opposition, that doing nothing is the best decision. On the other hand, if the test returns negative, we will expect a value of 117.4 individuals, because a negative test would convince us that translocating is the best decision. However, we don't know yet what the test will return. So we expect a value of 100 individuals multiplied by the overall probability of a positive test, including true and false positives, and a value of 117.4 individuals multiplied by the probability of a negative test, including true and false negatives. In total, after collecting the information, the expected value of the decision is 110.5 individuals. So again, the expected value of sample information is the difference between the expected value after running the test and the expected value of making the decision only on the prior belief. And remember that was 100 individuals. In total, doing the test increases our expected management outcome by 10.5 individuals, and that is the expected value of this sample information.